Welcome to another cosmology talk. This week we have Ryan Keeley, who is a postdoc at the Korea Astronomy and Space Science Institute. Today he'll be talking about a recent paper related to the H-naught problem, where him and his collaborators used a non-standard primordial power spectrum to mimic the changes of H-naught from the local value to the value you get from the CMB if you assume a power law, which is what lambda CDM does. I'd like to hear his thoughts on what I'm about to say, but I guess as a first choice solution to H-naught, it's maybe a little far-fetched because you do need to have a feature at exactly the right place to mimic H-naught. But the longer that H-naught problem goes on with any super well motivated solution that fits all of the data, the more worthwhile it is to look into the slightly less well motivated things. And nature has stumped us in the past. And if there is a feature, maybe it just happens to be there. And this is what everyone's trying to fit with all sorts of modifications of physics. It might just be that it's not a simple power law primordial power spectrum. If it isn't, then Ryan and his collaborators are onto something. Yeah, thanks, Ryan, for your time. Do you want to briefly introduce your work?
Sure, yeah. Like you mentioned, we essentially use a reconstruction technique to basically reconstruct a primordial power spectrum that can, by construction, fit essentially the high value of H0 from shoes or whatever, but still fit the Planck CMB just as well. Sort of along the line that you just said, because this is like a reconstruction, reconstructions will always be maybe sort of a priori less likely. People will naturally sort of assign subjective belief to them less than maybe something simple like a power law. I mean, I think that's sort of expected, but I mean, along the same lines, if there is no other solution, then maybe some sort of strange reconstruction thing like this might be the answer in the end.
Yeah, you could look at an inflation model that generates something that's similar to what you guys reconstructed.
Yeah, basically what we did in the paper. So once we have this sort of template that we got from doing the reconstruction, we were then able to sort of generalize that into essentially a model with essentially a new degree of freedom that characterizes how different from a power law this novel primordial power spectrum is. I think maybe one of the key statements that I think is maybe important for anyone watching or the community to maybe take away from this: inflationary models beyond like a simple single field slow roll inflation, or I guess similarly a power law primordial power spectrum, they're not the only game in town. This specific kind of featured power spectrum can fit the data just as well. And so if we're trying to make conclusions primarily on data, then at least as far as just the TT CMB angular power spectrum is concerned, this is still worth considering. The interesting reason to try to look for features or something non-trivial in the primordial power spectrum is that it has the potential to tell us something interesting about inflation. So people have mostly been talking about essentially single field slow roll inflation, and even simple modifications to this general sort of idea. They're usually always parameterized by some sort of power law, which is like an amplitude and a spectral index. But of course, that's not necessarily the most general thing you can write down, right? So potentially more complicated inflationary physics can yield these featured sort of primordial power spectrum. So any sort of potential that would have any sort of a kink or a step would generically produce wiggles or features that can potentially either confuse or give different inferences of AS background parameters. One particular example of this is what's been called wiggly whipped inflation, where there's essentially this large field inflation where essentially a non-trivial potential does give rise to these ringing features in the primordial power spectrum. The point is that this sort of ringing can be degenerate with sort of inferences of background parameters. This particular featured primordial power spectrum, we essentially derived it by a deconvolution method. So essentially, the way we generated this, we take the CL values from the best fit lambda CDM fit to the Planck dataset. And with these best fit CLs, you can essentially divide out or essentially deconvolve these radiative transport functions, these GL values. And so the specific algorithm that allows us to do this deconvolution is called like the modified Richardson-Lucy algorithm. A Richardson-Lucy algorithm is an iterative process that allows us to do any sort of deconvolution in general, but I guess we specifically had to modify it in this case to try to make sure that the power spectrum we got out was sort of physically meaningful. Things like the power spectrum itself had to be positive everywhere.
When I hear the phrase transfer function, I think of the thing that takes the primordial power spectrum and does all the physics that turns it into the angular power spectrum that we measure. Am I understanding transfer function correctly in your case as well?
Yeah.
So now that I've got the transfer function, how does that tell me the modified initial power spectrum?
Essentially, this transfer function, basically it just encodes all the background expansion history stuff. Maybe to zoom in on this sort of figure. It's a bit blurry on Keynote, but in any case. So each of these should be, I guess, a different GL of K for different Ls. And that's how it's modifying the power at different K values of the primordial power spectrum. to essentially transfer that into essentially power in an Elvin. So this thing itself basically only has information about the background cosmology, the expansion stuff. So yeah, it's just a mapping between, I guess, a primordial P of K to a CL.
What is confusing me, I guess, the thing that seems like the missing piece is I've got the transfer function. What do I use on the transfer function to get the primordial power spectrum?
In some sort of bin space, it's basically just like a summation over the CL is what the sum of K over GL of K times P of K. So you're essentially integrating out the dependence on K, and GL is I guess like a kernel.
But so we constructed GL using the red line rather than the blue data points. Is that right? On the top left-hand figure?
Yeah, this is essentially what we want to get out. We want to get out the red line again. This can normally be gotten by lambda CDM with H0 of 67, a transfer function that would result from that background cosmology, and then just a featureless power law. But instead, if you use the GL of Ks for like an H0 of 74, then when you essentially enforce getting back out the same red line, you necessarily have to get this non-trivial featured primordial power law out of it.
I see. So let me see if I've understood. So if one was to take the red line and take the Planck lambda CDM best fit parameters, find the modified, I've forgotten the next two people's names, algorithm, and apply it, you would just get back the power law.
Yeah.
The reconstructed thing would be the power law because it's the thing that got transferred to give the data with those cosmological parameters.
Yeah, that's right.
But if you change H naught, then you'll get a slightly different transfer function, and then you undo the transfer function of that red curve. The red curve doesn't have to be the best fit curve. That's just the best fit curve from lambda CDM. So I guess there's some potential even better fit.
Yeah, conceivably, yeah. Maybe to go slightly a bit more into it. So I guess this is the generic sort of algorithm. And sort of like you sort of brought up a slightly interesting point in that the most interesting way to use this sort of modified Richardson-Lucy algorithm is to do it on the data itself as opposed to like the best fit sort of thing. And so that's where I guess this sort of QL term comes in here, where you can use the covariance of the actual of the data themselves to try to get something that would necessarily fit better than essentially any sort of model you put in. That's not exactly what we did here. We did just use the best fit Planck to do the reconstruction. Maybe the takeaway here is that, especially for the CMB stuff, I guess I would just want to say that this modified Richardson-Lucy deconvolution is actually like a pretty interesting and useful technique to try to make as agnostic as possible inferences about background parameters from any sort of P of K. For anyone listening in the future, if you do want to go into it yourself and write your own MRL algorithm, these are the places to start looking. I like this sort of plot basically because it describes what's happening with this primordial power spectrum. So basically, if you just take a power law with H0 of 73, then you get this sort of blue line. So these are the CLs relative to the best fit Planck CLs. So with basically an H0 of 67. And so if you have a high value of H0 of 73 or so, then you get these blue line.
Is this then the best fit with H0 of 73? So the other lambda CDM parameters have been allowed to change?
Yeah.
So things like omega matter and stuff have been changed to find the best fit with H0 of 73.
Yeah.
Okay.
So basically, what happens here is that because you're changing H0, you're also changing the angular diameter distance to the CMB, which necessarily changes theta s. That different value of theta s basically shifts the entire set of acoustic peaks to different values, and that's basically what this ringing is. If you take this modified Richardson-Lucy derived primordial power spectrum and use the same initial background parameters as the best fit Planck, then you get this orange line, which, as you can see, is basically the ringing, but sort of 180 degrees different phase. And then if you do both changes, if you do the modified power spectrum and H0 of 73, then you get the green line, where essentially the ringing has been canceled out.
And why is the green line not exactly one? What is the algorithm failing to match?
I think that's basically due to numerical noise in the algorithm. Like you can see here, it's this sort of iterative procedure. And so essentially by stopping somewhere, then there's some sort of small amount of noise. I think this is a neat example of explaining what's happening with this. And so in the paper, we're sort of generalizing this class of things. And so by generalizing that, I basically just mean that we have this parameter f, which we use to interpolate between the best fit lambda CDM primordial power spectrum and this MRL, this modified Richardson-Lucy derived primordial power spectrum. And so then if f is this, again, this continuous parameter, which we can then use in sort of this Bayesian inference, we can then use this to calculate some sort of a Bayes factor to see if this additional degree of freedom is preferred or not. And similarly, we can just try to say, if we derive some sort of posterior for for F, whether F equals 1 corresponds to a power law, F equals 0 corresponds to MRL, whether the confidence ball seems to prefer 1 or 0, yeah, and in which case.
But one and 0 should have the exact equal goodness of fit, right? But almost by construction.
More or less, yeah.
And somewhere in the middle might be better or worse fit.
Yeah, up to this sort of, I guess, numerical noise from the algorithm, yeah, they should have basically the same. And sort of like you just mentioned, it's sort of interesting in that at about halfway between 0 and 1, at about, I guess it was about 0.6, that yeah, there's this marginal improvement to the TT likelihood. It's only about like a 2 sigma thing. You could sort of see that from the posterior here itself, right? In that it sort of peaks not at 0 and not at 1, and it's, I guess, slightly better at 0.6 or so. So the blue is with just TT, and the orange is with TT plus the H0 constraints. So with just the blue ones, then you have this marginal like 2 sigma improvement to the just the TT likelihood. As far as I can tell, when I sort of look at the residuals, it seems to basically just be sort of, I guess, fitting noise. So I guess I wouldn't try to make too much of a big deal about that. But I guess the interesting thing I think here is still just the fact that it's sort of degenerate. So yeah, statements about H0 from the CMB are sort of implicitly contingent on, I guess, assumptions about what the primordial power spectrum looks like.
One of the things that people are always making sure other people are careful about is that you can't just combine the CMB data with the H0 data, because when you assume a power law, because you then have inconsistent data. And yeah, you can derive parameter constraints after doing that, but they're kind of meaningless because there's a 5 sigma tension. But I guess with you guys, the blue contours are telling you, no, there isn't a 5 sigma tension. In fact, there's no tension at all because the error bars have widened so far.
Yeah, basically.
But then once you've got a model which is not tension between the two, then you can combine them.
Yeah. When I've been talking with people about H0 stuff before, it always has been sort of the case that, I guess, when they essentially add these extra degrees of freedom to, I guess, the CMB or whatever, essentially the error bars sort of just blow up a little bit, but the values don't change. So then when you add in like polarization data sets, then they sort of shrink again and the tension reemerges. So even just the fact that this is a large degeneracy, it seems a categorically different kind of situation. I'm not entirely sure how much of a deal I should make of this, but basically when you do include the H0 constraint, you can get like this Bayes factor where log of k is like 5.7, which is typically some sort of, I guess, like some very strong evidence that as far as the TT and H0 data sets are concerned, they really prefer this extra degree of freedom over lambda CDM.
Yeah, I mean, I guess that's not surprising. When you've got a 5 sigma discrepancy to play with, if you do something that allows the H0 value from the CMB to take these larger values without tension, you're going to get a big Bayes factor improvement like that.
So essentially there's this one new degree of freedom F. Essentially, by construction, for every value of this parameter F, there does exist a set of background parameters that you can get the same sort of likelihood out. So because I guess this kind of model is reconstructed as opposed to, I guess, something sort of a priori derived, then essentially the predictivity of it is kind of small. So you sort of necessarily get like this large Bayes factor. So it's, on some level, I feel it's slightly, I guess hacking your way to like this strong Bayes factor.
Yeah, I mean, I think of your paper as a kind of proof of concept rather than a model itself.
Sure, yeah.
It's showing that if a model existed that did this is the kind of amount of improvement that is open to such a model. And you're very honest in the paper, but it's still good to know that it's possible.
So yeah, so that's basically the main result of this paper. So I think the first thing that people might see when they see this sort of very featured non-trivial primordial power spectrum is that it's sort of just fitting noise, or it could still be on some level overfit per se. I guess I would argue that it's not just noise, basically because it has this sort of well-defined observable effect on, I guess, on theta S in particular. So essentially that figure 1 that I showed, because this sort of feature is changing like the pattern of the acoustic peaks.
I guess there's 2 questions of it being a better fit, right? Like one is it a better fit to the CMB alone? And there, I think the argument that maybe it's just fitting noise is perhaps quite compelling. But I think the vast majority of that Bayes factor is the fact that it's fitting the shoes data and the CMB simultaneously, which nothing else can do. That's definitely not noise. That's just allowing H0 to be a value that shoes wants.
Yeah. Preemptively reacting to potential criticism here.
I guess, unfortunately, the people who would give those criticisms aren't here, so we can't hear their perspective because I'm already persuaded. But leave a comment and we can have a discussion.
So on some level, I think your phrasing was sort of neat in that this is, on some level, I guess, a proof of concepts I think even for this idea of using like this model independent reconstructions to try to get at some sort of new idea or new physics, anytime you do a reconstruction, I guess the community at large will, I think, often sort of has this, I guess, negative subjective belief for essentially the results of any sort of reconstruction. And I guess the point that I would want to bring up maybe is that because this sort of reconstruction type of game, they necessarily fit the data just as well as compared to lambda CDM. And in this case, philosophical point that I would want to emphasize is just that prior subjective belief is probably not the thing we want to base firm conclusions on. So when you essentially have even sort of strange ideas that get the same sort of likelihood as lambda CDM, you don't want to rule out those ideas only on, I guess, prior arguments. So yeah, so in this case, I think the only way to then try to prove or disprove this sort of non-trivial reconstruction is to, I guess, look at new data sets. And that's the way to kill some novel idea.
I guess your particular reconstruction might get killed by new data sets, but presumably there'll always be whatever the new MRL-derived power spectrum would be. I mean, I think that there's a very clear distinction to make between looking at the CMB and seeing, oh, there's a little bit of a deficit of power on the large scale, and oh, maybe there's some feature at the small scales, then applying the MRL algorithm and going, oh, look, I've got a better fit. And at that point, yeah, okay, so one can take two paths there, and one can be just ignoring it because, yeah, okay, the MRL algorithm will fit noise. And the other one is to say, okay, can I think of an inflationary model that might mimic this behavior? And then I think reconstruction is valid because it's maybe turning on a lamppost saying, go look under that lamppost. It's not saying I have the model. But I think in your particular paper, it's doing something other than just that, which I think is interesting on its own. But this new thing is, as I said, the proof of concept. It's saying, look, this H0 tension is because you assumed a power law. And whether you think you're motivated in that or not is a separate question. But if you don't think it's motivated, then, okay, well, one can construct whatever particular power spectrum you want. And when you've got a 5 sigma tension, I think this sort of thing becomes a lot more valid. And when every other model that's trying to explain this is failing, even something like this, which is kind of like impossible to fail because by construction, you make H0 bigger and then find the power spectrum that fits the data. The fact that that's possible is worth keeping in mind. Although I think I do agree with the idea that this particular reconstructed power spectrum is maybe not necessarily super well motivated, but not so much because I'm wedded to a power law, but more just because it feels like it must be some sort of crazy coincidence that there was a feature. The existence of a feature isn't the problem. It's the fact that there is a feature that just so happens to affect the primordial power spectrum such that humans observing the CMB now would see that to be almost exactly the same as a shift in the value of the expansion rate. That seems like very anthropic. But again, like when nothing else is working, yeah, I mean, if that feature happened to be there, that's exactly what would happen. We would measure the expansion rate and we get a slightly different value.
Yeah. So aside from this sort of stuff about priors, I guess maybe the last thing that we did in this paper is try to take this sort of noisy, very strange looking power law and see if we could sort of try to, I guess, like filter it to something that might look slightly more reasonable. And basically to do that, we basically just take, I guess, a low pass filter and apply it to the entire power spectrum and then put that back into class and see if the CLs get the same sort of likelihood. In general, if you play this sort of scheme, then for any sort of, I guess, cutoff frequency, it seems to only get slightly worse. And in this case, the orange is basically at the level of, I guess, only like a delta log likelihood of of about 0.3 or so worse. That's essentially what you get from the orange, and it still looks sort of smooth. There's these sort of weird features at like the heights of the these oscillation features get wiped away, and it gets sort of I guess more regularized. So as in something that could actually reasonably come from maybe like a step or a kink in an inflationary potential. And sort of at the same time, we were trying to answer, if we have this very complicated looking primordial power spectrum, what are the actual features in this that are sort of doing the actual physics? Sort of obviously, it was always going to be sort of something in this range, something between, I guess, 0.01 in K, something like 0.025 in K, simply because those are the K values that map up to L of 2500. So basically, anything above K of 0.025, you can basically just filter away completely. These sort of, I guess, smaller, higher frequency features don't really seem to matter at all.
And that's just because the CMB doesn't have that much information.
So I guess the likelihoods are basically only sensitive to the up to the 2500 L mode. So yeah, so I guess if you can sort of visually see, I guess like this orange plus basically like a straight line or the green after 0.25, that would be some sort of perhaps a priori most likely kind of primordial power spectrum, which still achieves the same sort of shifting in theta s.
And is the black line the power law lambda CDM?
Yeah.
So are you predicting a boost in primordial power on small scales then for some reason? Because that green line is quite a bit above the black line.
That would be sort of, I guess, the next step is to sort of try to apply this kind of featured primordial power spectrum to other data sets. I mean, the first one would naturally be the polarization. But yeah, for the matter power spectrum, like you said, because there's this sort of extra power at high K.
Why is there extra power at high K? I'm a bit confused by that because or is there not? Like, because if the data isn't restrictive there, could the green line be kind of anywhere there?
So yeah, so I think the green line, like you said, could be basically anywhere. I guess I think the simple reason why this is here is I think the likelihoods are different here. I think these kind of features are just noise, as that comes from just the algorithm.
Because with the power law, it would make a prediction about K of 0.35 based on information at K of 0.1, but a reconstructive algorithm would be like, I'm completely agnostic about 0.35, it could be anything. So maybe I was too strong to say that you guys are predicting a bigger power spectrum there because you're just not predicting anything there. Like it could be dragon.
Yeah, I think that's the fairest thing to say is that this reconstruction really shouldn't say anything about K modes above 0.25.
Which is sort of what you are saying by, you're filtering it, but you could maybe make an even stronger one of just adding a step there or something and seeing that it still doesn't change the likelihood much, I guess. Yeah. I guess having said that though, even on the scales of, 0.1 for K, there are measurements of the matter power spectrum. So it'll be very interesting to see whether these features affect the CMB differently to how they would affect the matter power spectrum. Because I would naively think they would. Because the kind of degeneracy between H0 and these features will be different in the matter power spectrum than it is in the CMB. So it might, or at least naively, I think that maybe it isn't. But so then, yeah, like I guess the BAO oscillations should look slightly different and maybe have a different amplitude or something. I'm not sure.
Yeah. So like I said, that's sort of the next step in a corollary to sort of the sort of H0 story. Basically, if you calibrate the supernova on the high value, choose value of H0, right? But then you calibrate the BAO distances on the, I guess, lambda CDM constraint to the CMB, like, and have that R drag of 147. Even then, like the distances themselves are discrepant on sort of similar significance to the H0 tension. And so I guess similarly, because this feature will necessarily change the inference of R drag to it, if I remember correctly, to lower values, then in the same way that would predict the BAO derived distances, I guess, downwards towards the supernova ones. But there could be a potentially more complicated story as well, where the actual feature in the matter power spectrum that you're fitting itself could look different because of these sort of non-trivial features.
That was what I was thinking. Although there's one thing that I don't think you mentioned in the paper that I thought benefited you, because there's this mild omega matter sigma 8 kind of tension where I think the local measurements prefer a slightly smaller omega matter. And it looked to me that when you interpolate from F of 1, cold dark matter density decreases a little, which I think I might be completely wrong here. So again, if I'm wrong, write it in the comments. But I think that actually reduces the tension a little bit with the local measurements that get a slightly smaller value of power on the small scales. Most of the other attempts to solve the H0 problem fall into trouble for exactly that reason, that like early dark energy or something can fit H0 slightly better, but then this S8 tension gets much worse. And it looked to me like you would actually improve the S8 tension.
Yeah, I'll I guess look into that one and then here, but yeah. So the last slide I had is just the conclusion slide. So yeah, you can solve or reconstruct the H0 tension via these specific features. Like I mentioned at the beginning, I guess maybe one of the interesting takeaways is that a power law primordial power spectrum isn't the only game in town. And I guess as a necessary corollary to that, potentially we should start to try to think of inflationary physics beyond, like, I think a single field slow roll inflation. Since I wrote this paper, a few people have come back to me, like pointing out some code that they have, where if you can take a primordial power spectrum and then essentially turn the crank on that to try to come out with inflationary parameters of the potential. So, I mean, in some sense, we could not just reconstruct the primordial power spectrum, we could try to reconstruct the inflationary potential itself from, I guess, a CMB plus H0.
So the next question, which I think you've covered to some extent, but you can go into more detail, where to next? So I guess the obvious thing is stuff you've already said is fitting to the polarization and checking what implications there are for the matter power spectrum and BAO and stuff. And then also like trying to find the inflationary model. But are there any other avenues that you're exploring next?
So yeah, as far as I guess this specific I guess model that's basically next. But I guess in the larger game of trying to I guess try to look for features in the in the power spectrum, there's a few other sort of I guess techniques that can be done. There's always sort of like the question of trying to I guess answer the question, trying to see if sort of in a model independent way if the temperature and polarization data themselves are sort of necessarily consistent. To be slightly more specific about that is that beyond this modified Richardson-Lucy deconvolution stuff, you can do, I guess, a Gaussian process reconstruction on the primordial power spectrum. Basically, the game there is that if you can take some sort of Gaussian process reconstruction from the TT data set and then use that to try to do some analysis to, I guess, make predictions for the polarization data sets and see if they sort of come out the same. And that would be essentially this model independent consistency test.
Yeah. It feels to me like it would surprise me if it didn't just pass that consistency test quite comfortably. But okay, I mean, like that means if it doesn't pass it, then it's super interesting. So like, I mean, consistency tests are certainly never a bad thing to do.
And similarly, from this Gaussian process reconstruction, we could basically find the same sort of feature primordial power spectrum. And I guess this Gaussian process reconstruction can generate essentially a large class of essentially random features that basically can be sort of checked simultaneously. So I think that's a useful technique to try to find in general any other sort of class of features that could be interesting.
Cool. So last question, I ask everyone, outside of your own research, what do you think is the most interesting thing in cosmology at the moment?
Maybe the outside of my own research is like slightly it's slightly hard to answer since I do kind of work on a lot of things.
50% of people have just said outside of the thing I'm currently talking about, but I actually work on it. So feel free.
I guess a lot of what I've been doing recently is sort of, I guess, trying to test lambda CDM in various ways. But I guess sort of outside of that, I guess is I'm still always interested in, I guess, the question of what is dark matter, trying to answer about whether it's WIMPs or axions or stern neutrinos. So yeah, so I guess I've been thinking a bit about, I guess local group sort of, I guess, cosmology, trying to look at the physics of dwarf satellite galaxies and try to see if they're more consistent with some sort of self-interacting dark matter or just plain lens whole dark matter.
Awesome. Cool. Well, thanks everyone for watching. If you like this, please subscribe, click the bell, and you'll be notified of new videos. Click like to help with the YouTube algorithms and share the channel with your colleagues. If you have any questions or suggestions, leave a comment. I'll make sure Ryan sees them. While you're here, you can watch another video. I guess the most relevant one is probably either the one by Colin Hill, where he was talking about why early dark energy doesn't solve the H0 problem, or the one by Adam Rees where he was talking about why Cepheid crowding doesn't solve the H0 problem. So a very theoretical, this doesn't solve the H0 problem, and a very experimental, this doesn't solve the H0 problem. And yeah, thanks again, Ryan, for the great talk.
Sure. Thanks for having me.